Hi, this is our project on estimating ground level ozone.
So ground level ozone is of particular interest to us because of the negative health and environmental impacts it poses. It's linked to respiratory, metabolic, and reproductive issues and is known to cause considerable damage to vegetation. So one way we measure ground level ozone is through ground monitoring stations, which is used a lot by governmental agencies. However, they are expensive to set up and they're lacking presence in rural and underdeveloped areas. So in developing regions, actually, there's an inadequate amount of ground monitoring stations. So therefore, there's a lack of comprehensive air quality data in those regions.
On the flip side, you have satellite data, which has near total spatial coverage, but it only measures vertical column density, or VCD. This includes both helpful stratospheric ozone and harmful tropospheric ozone, so while it's certainly helpful, it's definitely not an accurate proxy for ground level ozone. So in order to get around this, we aim to use machine learning methods to estimate ground level ozone, using the VCD we just mentioned, as well as auxiliary variables like meteorological, chemical, and land use data, all of which affect ozone formation. For the machine learning methods, we use multiple linear regression and random forest regression.
So more on our input variables. For our meteorological variables, we selected solar radiation, maximum temperature and precipitation, and vapor pressure as our input variables. And then for our land use variables, we decided to select NDVI. And then for our VCD data, we chose precursors of ground level ozone, which include nitrogen dioxide, formaldehyde, and carbon monoxide. And we also included the column of ozone, total ozone, with stratospheric and tropospheric ozone itself. So here is our input variables as time series, and then this is their spatial distribution.
So this is a workflow diagram of how our project worked. We started with input data sets from Google Earth Engine from a variety of sources, and we then consolidated them into one single table. And this was done in a way where you can imagine each row in the table as a stack of pixels over a ground level measurement, as you can see from the X's in the bottom left. From here, once we had the data set, we evaluated the accuracy of different models using a trend test split and accuracy metrics. Our study area was in Southern California. We chose these 8 locations, and on the right is the same data in the tabular format. For our results for linear regression, we achieved a pretty low mean absolute error of 11.4 micrograms per cubic meter and an RMSE of 14.3 micrograms per cubic meter. Our random forest regressor did significantly better with a mean absolute error of just 9.78 micrograms per cubic meter and an RMSE of around 12.3. Our R-squared value, which determines the correlation of input to output, was around 0.46. However, the study had its limitations that we want to acknowledge, mainly that the study area was in Southern California, making it harder to evaluate the impact of things like precipitation and humidity, because there simply isn't a lot of rain in Southern California. Our training data set was substantial, around 5,000 points, but it was still relatively small, and we'd need it to be bigger to try more complex machine learning approaches. We also had very little time to put this project together, and in the future, we're considering incorporating more variables.
So Purva and I would like to give a big thank you to NASA Seas, especially the entire Air Quality Initiative team. And this was all made possible by the amazing mentorship, especially Juthi, Dr. Jiang, and Dr. C. Thank you so much for your invaluable time and mentorship.
So despite all of this wonderful support, we did run into some challenges, mainly downloading and visualizing relevant geospatial data, especially without any formal GIS training. We ended up turning to Google Earth Engine for this reason. And another issue that we encountered a little bit earlier on was just understanding the problem space as a whole. However, we do want to thank NASA Seas for all the skills that we came away with. For me, that mainly means diving more into geospatial data analytics, and I'm eager to continue looking for ways to do impactful research in the future.
So for me, coming from a chemistry background, during the background reading, I was able to expand my knowledge of atmospheric chemistry, and I'm eager to further my knowledge in environmental and atmospheric chemistry.
Thank you so much.